Well, pre-calculus classes, as always, good morning, good afternoon, or good evening. We are getting towards the end of what we actually cover from Unit 10 with Section 10.3. We have 10.3, and then we do skip over 10.4, cover a little bit out of 10.5, and then wrap that up here to in the school year for second semester. But what we're going to look at in 10.3 are what we call geometric sequences and series. There are two distinct patterns that we really focus on, and certainly you might even come to next year if you are taking calculus. But the arithmetic sequences are the patterns that add or subtract a set number each time. The geometric sequences are sequences whose consecutive terms have a common ratio, meaning they either multiply or, in theory, divide by a set amount as well. And so we do have a little bit different terminology. Unlike the arithmetic, where we used a sub n, for the geometric, we are going to use g sub n equals, again, g sub 1 is your first term, and then r is that ratio, or you might even hear it as just the term rate. So as the notes go, those two terms are used certainly interchangeably if you see those. So again, your explicit formula and then your recursive formula. Again, you always define the first term. Then it's just that previous term, g sub n minus 1 times the rate. And again, that only applies to term 2 and up. So if we look at example 1 here, where our sequence goes 5, 15, 45, and so on. First thing we're always going to do is look at, okay, well, what is the pattern? Well, the pattern is, from 5 to 15, 15 to 45. It's certainly not adding by a set amount. It's multiplying with a rate of 3. So as far as explicit formula and recursive, neither one of these, unlike arithmetic, really have any work. So for the explicit, g sub n equals, first term is 5 times 3 to the n minus 1. For your recursive, g sub 1 equals, again, we always have to define that first term, otherwise you can't use that prior term. G sub n equals, again, the rate 3 times g sub n minus 1. And again, n has to be greater than or equal to 2. Now, as far as, using one of these to find the 15th term, again, we don't want to actually use all the way out to term 15, so we don't really want to use that recursion philosophy. So what we'll do, g sub 15 equals 5 times 3 to the 15 minus 1 is 14. With these, you are going to end up with probably a pretty big number there when we take 5 times 3 to the 14th. Yeah, 23,914,845. So basically, if you think back to first semester when we were working with exponential and logarithmic formulas, a geometric sequence is essentially an exponential growth equation. So there is your 15th term. So that's kind of the basics of a geometric sequence. I know the next example is just, again, kind of a little different, term here. Find the sum of the finite geometric series. So again, what we're going to do is starting at term 1 to term 5. Well, if you plug 1 in, 5 times 2 is 10. So here is term 1. Then when you do to the second, 4 times 5 is 20. We'll even talk a little bit about what the pattern is when you plug into the third. 2 to the third is 8 times 5 is 40. So right now you may even see what the pattern is. Well, 10, 20, 40 is doubling. That's essentially what the 2 there represents. So if we do the fourth term, 2 to the fourth is 16 times 5 is 80. Or again, you can simply use the pattern. The last one there is 160. So 30, 70, 150, 310. And then here in a little bit, we're even going to show you the formula that you can use so you're not actually having to write out all 5 of those terms and solving individually. So there's, again, another geometric series sequence type problem. One other before we do move into really defining how the geometric series works is here. If we give you, we ask you to find the 14th term. 4th term is 125. 10th term is 125 over 64. Now, unlike in 10.2, where we had you subtract and then divide to get that difference amount, now we're dealing with a ratio or rate. Well, you can see term 4 is 125, term 10 is 125 over 64. So what we're going to do, we are still going to subtract, except now the ratio 10 minus 4 will equal, to figure out the ratio instead of subtracting these, we're going to have to divide those. And so if you take this one divided by this one, again, you take here we took the later term subtracted from, or subtract the prior term. Now we're going to take 125 over 64 divided by 125. Now, when I work this out, I kind of think, okay, going back to first semester complex fraction, make that 125 over 1. So r to the 6th will equal 125 over 64, multiplied by the reciprocal. So r to the 6th is 1 over 64. We'll now take the 6th root, which when we do that is 0.5 or a half. So our rate is 1/2. Now we can use one of these two values. Again, you can pick, I know I certainly, if I'm going to figure out the first term, I'm going to use the easier value, 125. So g sub n equals g sub 1 times r to the n minus 1. That's our general formula. 4th term is 125. Again, we don't know our first term. 1/2 to the, since we're using the 4th term, 4 minus 1, so 125 equals the first term times 1/2 to the 3rd, which is 1/8. Now, as far as canceling that out, multiply by the reciprocal, 125 times 8 is 1,000. So there is your first term. We have our rate. Now if we want to find the 14th term, g sub n equals first term times 1/2 to the 14 minus 1 is 13. Now, as far as what we get, let's see if this will do a conversion for us. 125 over 1,024. And I guess we can even say that's the 14th term. So there are geometric sequences. Geometric series is where we're simply going to take these concepts and multiply instead, or use the sums instead. Well, sum of a finite geometric series, the sum, again, when you see that capital S, that's just kind of another interchangeable form for sum. First term times 1 minus the rate to however many terms you're using, divided by 1 minus the rate. So, for example 1, we're starting, our index is 1 to 10, so basically it's saying add up the first 10 terms. Well, in order to do that, to get our first term, you plug 1 in for n. So the first term is basically 4 times 0.3, which is 1.2. So our first term, 1.2 times 1 minus this value that has the exponent is your rate. So we're going to take 0.3 to the, since we want 10 terms, 1 to 10, over 1 minus 0.3. Main thing you have to watch with these is just kind of how you're entering things into your calculator. So we're going to do one. I actually almost prefer to enter this in first. So 1 minus 0.3 to the 10th, and I'm going to go ahead and hit enter, then divide by that 1 minus 0.3, which is that value, then multiply by the first term. And again, one of the things I always will do is if it will, there, this one apparently is not going to convert to a fraction. It's a little more complex of a fraction than our calculator is going to allow. So it's around 1.7. Certainly as you work through things on Pearson, they'll probably tell you how far they want you to round if it's something that you can't actually get as a fraction. Now, example 2 here, a little different in that now they're telling us find the sum. They give us the last term, so we actually have to figure out how many terms there are. Well, you can look from 2 to 6 to 18. Find the pattern. Well, from 2 to 6, the rate is 3. So what we have to do is figure out, okay, which term is 486. So what we'll do, G sub n equals, which we'll actually plug a number in there in a moment, but it's going to be, first term is 2, rate is 3 to the n minus 1. This term, 486, equals 2 times 3 to the n minus 1. Now what we can do, divide by 2. So 486 divided by 2, when you actually divide that out, is 243 equals 3 to the n minus 1. Now, going back to first semester, when that exponent is actually the variable. Now, yeah, here you probably could figure out just, with a little bit of calculator, what power of 3 is 243. If you're ever given something that's not really easy to work with, the way we're going to work with that is we are going to actually have to take the log of each side. And the reason we do that, that allows us to move the exponent out to the front and then divide log 3 over. And so when you do that, log 243 divided by log 3 is 5. So n minus 1 equals 5, so n is 6. Now we can come back up and actually use, we're going to add up s of 6. First term was 2. 1 minus the rate is 3 to the 6th over 1 minus 3. And now we can multiply this out again. With especially the older TI models like my 83, I do actually prefer go ahead and do that and then divided by, well, here just 1 minus 3 is negative 2, and then multiply by 2, 728 would be the sum of the first 6 terms. Geometric series have a tendency, they will get pretty big pretty quickly, so that's the the reason that even only 6 terms you can see that sixth term is already getting pretty big. So, only other topic that does come up with these is if we have an infinite series. Now, if the rate is less than 1, now it can be a negative or a positive, you can actually find the theoretical sum that this is going to approach. Now, you won't technically get the true sum, but because the decimal values, if the rate's below 1, they do get smaller and smaller. There is a number that it approaches. And this actually comes from this formula. Basically, what's happening is if the rate is below 1, you're essentially ignoring this value right here. So, find the infinite sum of 4 to the 0.6 to the n minus 1. So again, the infinite sum, first term, again, if you plug 1 in, well, if I take 0.6 to the 0, anything to the 0 drops out. So our first term is 4 over 1 minus this value right here is your rate. And when I do that, 4 minus, well, 1 minus 0.6 is 0.4. 4 divided by 0.4 is 10. So, if you were to initially write these out, you're going to have 4, 2.4, some other decimals. As you add those decimals that will get smaller and smaller up, you're going to get values that approach 10. So that's kind of how things are a little different if you have what we call that infinite sum or series. All right, another one. Again, here's where 3 plus 0.3 plus 0.03 plus 0.003 plus 0.0003 and so on. This is an infinite sum. Even though these are continuing on forever, they are getting smaller and smaller. There is a value these are going to get really close to. So what we have to do, we know the first term is 3 over 1 minus. Now to figure out the rate, all you actually have to do is take one term divided by the prior term. And when you do that, 0.3 divided by 3 is 0.1 or 1/10. It's kind of up to you. 1/10 will eventually convert this back to a fraction. But when you're actually initially entering things into the calculator, you're going to find it much easier to do this. So 3 divided by 1 minus 0.1 or 0.9 is 3.3 repeating, which when we convert that to a fraction is 10 over 3. So again, if you were to keep adding, because basically, hopefully that makes sense, all you're doing is each time you're adding that additional, that's where the 3.3 repeating comes from. So it's 3 and 1/3, which if you actually add that up is 10/3. So that's, if you had advanced studies algebra 2, I think you guys worked with actually finding how you derive those repeating decimal equivalents. That's essentially what we're doing right here with this. All right, one final example, and then that'll actually be it for 10.3, a little bit longer section. Right here it says a ball is dropped from a height of 20 feet. It rebounds 60% after each bounce. Find the total distance traveled by the ball. So this one is actually kind of tricky. So it's kind of like we're saying, okay, well, you have the ball here. Here's the ground. It is dropped from a height of 20 feet. And then it rebounds 60% after each bounce. Well, the reason why I say this is tricky is 20% or 60% of 20. So it drops 20. It bounces up 12. and then back down 12. Then it's going to, and again, we're not going to do every last one of these, but then it bounces back up 7.2 and down 7.2. Well, the reason why I do this is you essentially have two separate sequences, series. You have a series for the bounces up. There is a series for the bounces down plus this 20. So what we actually do is we are finding 20 plus two separate infinite series. And so we'll actually talk about that here in a moment. And so that infinite series, now again, yes, eventually gravity is going to take that ball bouncing up and down and it will stop. But your first term we actually view as the 12 divided by 1 minus that rate of 0.6. So we have 20 plus 2 times 12 divided by 0.4, which is 30. So again, in theory, between bouncing up and down, the ball is going to bounce roughly 80 feet. This is one that is a little trickier. And again, it's because you do have to view it as, okay, it's bouncing both up and down along with that initial drop. So this does wrap up 10.3, a little bit longer section than the first two.